So, so these are the contents of today's presentation. I'm going to start from an introduction. Then I will talk about our proposed method, which is quantum annealing for flow computation. And we've got two proposed methods today. The one of them is actually for one of them we published a journal paper, and the second method is a kind of the main subject of today's presentation, and conclusions are given at the end of the presentation. So introduction, as you know, there are two types of the quantum computers now. One is a gate-based quantum computer, and the other one is quantum annealing computer. And today we focus on the quantum annealing computer, but we do, in our research group, we work for both gate-based quantum computer and the quantum annealing computer, but today focus on the quantum annealing. So, gate-based quantum computer are highly versatile. So, you can use that gate-based quantum computer for universal applications by using a vector and matrix operations. And when you do Google, you can find a fair amount of the prior research on flow computation, for gate-based quantum computer. But for quantum annealing computer, these are specialized in combinatorial optimization problems. So what you can solve is either Kubo model or Ising model. So these are the cost functions. In the Kubo model, you have 0 or 1. And in the Ising model, you have -1 or 1. But these equations are equivalent. So what you can obtain by quantum annealing is the optimum solution, which minimizes the combination of xi or sigma I, which minimizes these cost functions. That's it. So these cost functions very different from Navier-Stokes equations. That's why when you do Google, you cannot find many research about flow computation for quantum annealing. So as far as I know, there are just only two prior studies studying flow computation, and one of them is our work, our recent work. So I will explain it later. So I'm going to talk about the proposed quantum annealing method, but before talking about our method, we start from the three-step strategy to construct quantum annealing method for flow computation. So we focus on the Kubo model today, so not Ising, but these are equivalent. So we focus on the Kubo model. So our proposed methods developed such that the physical correct solution of xi satisfy exi equals 0, makes cost function equals 0. Following a three-step, the first step is the discretized governing equations as usual. For example, in the finite difference method, when you are given this derivative in the finite difference method, you may discretize this derivative like this. And in matrix notation, you may write AU equal B or AU minus B equals 0. And A is a coefficient matrix, U is a velocity in this example, B is a constant number or something like a pressure gradient. And the second step, convert fluid variables to binary, because what you can deal with in the quantum computation is 0 or 1, 1 minus 1 or 1. So you have here real valued number here. In this case, you have velocity. So you have to convert real valued number into binary. So today we use this conversion, but you don't need to use this. You may use different conversion, but what we want to have is binary numbers. Then when you convert U to X, which is 0 or 1, then this coefficient matrix changes to A tilde, A tilde, but just very simple calculation. Now, third step is build a Kubo model from the binary governing equations. What we do in the third step is simple, just square this equation, because the Kubo is a quadratic equation. So we just square this binary governing equations and set as a cost function. That's it. So the proposed method 1, quantum annealing lattice gas automata. So as I said, we published a journal paper recently about this method, QA-LGA. So what is a LGA? Actually, this is almost the same as LBM, as you explained it. So actually, LBM was developed from LGA. So in the LGA, we consider hexagonal computation grid. And in this example, Actually, particle state is explained by just 0 or 1, existence or absence. So in this case, you have second, third, the sixth direction particles. So in this case, you can write xi equals 0, 1, 1, 0, 0, 1. So obviously the LGA is suitable for quantum computation. And time evolution, as he explained it, we have collision state and the propagation or streaming state. So at the collision state, the particle direction changes according to the collision law. And at the propagation state, the particle propagates along the lattice line. So it's very simple. And in LGA, we do the same steps as like LBM. So in this time, evolution can be written by this equation. So xi plus something. This is collision function according to collision law. And this collision function holds these two equations, but I will explain you the meaning of these equations later. And now we have a CI here. CI is a lattice velocity. And in the components, you can write UI and VI like this. This is a xi direction velocity component. This is, eta direction velocity component. You may think this is xy, but we use x here, so we cannot use xy. We use xi and eta instead. So the important point here is we have a time evolution equation here and the equations for collision function. Using these three equations, we can obtain these two conservation equations. So these equations are actually quite obvious. For example, in the mass conservation, this equation says the number of particles should be the same before and after the collision. So same conservation should be satisfied for momentum conservation. So we focus on these conservation equations to develop our quantum annealing methods. So we're coming back to three-step strategy. The first step is discretized governing equation. Second step is convert fluid variables to binary. Third step is build a Kubo model. But when we see that these LGA equations, these equations are discretized already. And also the particle state is explained by binary. That means we have done first and second step. So what we need to do for LGA is only the third step. So build a Kubo model using these two equations. So again, we use these two conservation equations, but we focus on collision today because the collision determines the physics. So to just simplify the discussion, we focus on the collision. Then we introduce Ti prime, which is the time after the collision. So what we want to get is the particle state after the collision at the same location. So we do we make the Kubo using these two equations. The same equation here, but instead of writing xi ti prime r, I just simplify the notation as a xi prime. So what we want to get is the particle state after the collision, which is xi prime. And by summing these xi prime, xi, we can obtain zero or something. This is constant number. Then from this relation, we can obtain this relation, then square the both sides of this equation. We do the same thing for the momentum. But for the momentum, we decompose this direction into xi and the eta direction, but simple, just decompose it. And we have ui and vi here. So these are the components of CI, the simple xi direction, the eta direction velocities. And from here, we obtain the same relation like mass, then square these two equations. So what we want to get is the xi prime, which is the particle state after the collision, and the xi prime should satisfy these three equations. So our cost function is simple, just adding these three set as a cost function. So if you can minimize, if you can get ex equals 0, cost function makes 0, then that xi prime satisfies these conservation equations. So we expand each term then the orange terms corresponds to Qij. This is your cube matrix. So these are okay, but not sufficient. The reason is Xi, which is pre-collision state, also satisfies conservations. So what we want to get is Xi prime, not Xi, right? So we add additional constraints at the first time to obtain the Xi prime, which is different from Xi. Then we just solve, we just put this equation into quantum annealing. You can obtain the flow computation. So as an example, we solved 1D channel flow. Reynolds number is 40. Unfortunately, we cannot do that, large scale computation yet. But this is it's kind of the first step to obtain the flow solution using quantum annealing, because a lot of people in computational scientists said it's almost impossible to run the flow computation using quantum annealing, but it's a first step, but it's possible. So now I'm talking about the second proposed method. This is a kind of the main subject of today's presentation. So quantum annealing computation algorithms to obtain converged flow solutions. We developed this method for both LGA and finite difference method, but we focus on the finite difference method today due to the time of the presentation. So actually, the conventional computation, what we tend to do is starting from initial condition and run the time integration or convergence calculations to obtain the convergent flow solution. But what we want to do is actually we focus on the quantum superposition state. So at the quantum superposition state, you have all the solution candidates, at initial constant. So you have everything. And also you have a convergent solution as well. So what we want to do is just extract using quantum annealing, just extract the convergent solution without you doing any time integration. So this is our idea. So to do this, we follow a three-step strategy. The first step, as an example, we do the just 1D channel flow. And the first step is discretize governing equations. So these are the equations of the mass and the momentum. But for the 1D channel flow, you can simplify these equations like this. It's very simple. And one of the points here is that we assume steady flow, because we assume converged solution equals steady solution. So we just ignore the time derivative term. Then we discretize this governing equation, and this is the discretized governing equations. And the matrix notation, you can write A equal B, and A is a coefficient matrix, U is a velocity, B is here pressure gradient. So this is constant number. Another point is here, in A, the boundary condition is already contained. Convert fluid variables to binary. This is the second step. So again, we use this conversion, but what we want to get is just a binary number. So you may use a different binary conversion. So from A equal B, we convert to binary, then we can get A to the X equal B. So A matrix changes to A tilde, but this is just a simple computation. Because when you use this conversion, this A changes to A to the X due to the change of the U to X. But so X is a binary number, the B is the same. And the third step, build a cube model from the binary governing equation. So this is your binary governing equations. Again, we square the both sides of this equation and set as a cost function. Then we solve this equation. Just put it into the quantum annealing. Then we obtain this, velocity profile. We just succeeded in extracting a solution from the 10 to 14th power solution candidates. Unfortunately, we cannot do that in a large scale computation yet. Okay, but this is the first step to use another first step to obtain the flow solution using quantum annealing. Yeah, okay. You mean the time, right? Yeah. Okay. Yeah, conclusions. Yeah. So conclusions. I introduced you two proposed method, first and second. So we published a journal paper for QLGA, and the second one is kind of our main subject of today's presentation. And when we developed the quantum annealing method, we followed three steps showing here. And to obtain the converged solution, we assume the converged flow solution is the same as steady solution. Then we ignore the time derivative. So what we have to do next is future challenges to expand the computation scale and reduce errors. So that's it. Thank you.